Every single day, the Pacific Ocean holds 710 million cubic kilometers of water against the California coastline. And every single day, 39 million Californians go thirsty. Not literally, not yet, but the trajectory is undeniable. The data is unambiguous, and the engineers who have spent their careers studying it will tell you, quietly, carefully, with the measured language of people who deal in facts rather than panic, that what is coming for California's water supply is not a crisis, it is a collapse. The numbers demand attention. The Colorado River, which supplies water to 40 million people across 7 U.S. states and 2 Mexican states, has lost 20% of its average annual flow since the year 2000. Lake Mead, the largest reservoir in the United States by volume, dropped to 27% of capacity in 2022, its lowest level since it was first filled in 1937. The Sierra Nevada snowpack, which historically supplied 30% of California's annual water needs by melting slowly through spring and early summer, is projected to decline by 65% before 2100 under moderate climate change scenarios. And paleoclimatology studies of ancient tree rings reveal that the American Southwest is currently experiencing what researchers at UCLA have called a megadrought, a sustained dry period that, in its natural historical form, can last not years, not decades, but 1,200 years. 19 meters below the surface of the Pacific Ocean, less than 1 kilometer from the California shoreline, engineers are proposing to sink intake pipes the diameter of a city block. From those intakes, the most powerful seawater desalination system ever conceived would pull 5 billion liters of ocean water every single day, treating it, purifying it, mineralizing it, and pumping it 600 kilometers inland through a pressurized pipeline network to the cities, farms, and aquifers of a state that the climate has decided to abandon. The price tag? $3.5 trillion over 30 years. The alternative? None. Join QuitTech Process as we uncover the secrets behind this engineering marvel. The life cycle and economics, the arithmetic of thirst. The economics of California's water crisis are not complicated, they are simply staggering. California's agricultural sector, the most productive in the United States, generating $59 billion in crop revenue annually and supplying more than a third of the country's vegetables and 2/3 of its fruits and nuts, consumes approximately 80% of the state's developed water supply. Every 1% reduction in agricultural water availability costs the California farm economy between $800 million and $1.2 billion annually in lost production, fallowed land, and destroyed permanent crops. The orchards and vineyards that take 5 to 10 years to establish and cannot simply be replanted when water returns. The human water supply dimension is equally acute. The State Water Project, the network of reservoirs, aqueducts, and pumping stations that California built between 1960 and 1990 at a cost of $4 billion, was designed to deliver 5.4 billion cubic meters of water annually to 27 Californians. Today, it serves 39 million. In critically dry years, it delivers less than 5% of its contracted supply. The infrastructure that was built for a climate that no longer exists is failing a population that has nowhere else to go. The economic case for the proposed Pacific Desalination Network rests on a comparison that California's Department of Water Resources has made explicit. The cost of building and operating the full desalination system over 30 years, $3.5 trillion, is lower than the projected economic damage of doing nothing. A 2023 study by the Rand Corporation estimated that water scarcity under continued drought conditions would reduce California's GDP by $1.1 trillion per decade by 2050, eliminate 680,000 agricultural jobs, and trigger the largest internal migration in American history as the Central Valley, home to 4 million people, becomes economically uninhabitable. $3.5 trillion is not the cost of ambition. It is the cost of survival. The technology that makes the investment viable has matured dramatically over the past 2 decades. Seawater reverse osmosis, the process at the heart of the proposed system, has seen its energy cost per cubic meter of produced water fall from $3.50 in 2000 to $0.65 in 2023, driven by advances in high-pressure membrane technology, pressure energy recovery devices, and large-scale system integration. The world's largest existing desalination plant, the Ras Al Khair facility in Saudi Arabia, produces 1.025 billion liters per day from a single site. California's proposed network, at 5 billion liters per day from multiple coastal facilities, represents a 5-fold scaling of a technology that already works. The engineering challenge is not whether it can be done, it is how fast. Step-by-step technical breakdown. How you pump the Pacific. The California Pacific Desalination Network, as proposed in the most comprehensive engineering concept study to date, operates through 5 integrated stages that together transform raw Pacific Ocean seawater into drinking water, agricultural supply, and aquifer recharge at a scale no nation has ever attempted. Stage 1. Offshore intake infrastructure. The process begins not on the coast, but 900 meters offshore, in 19 meters of water, where velocity cap intake structures, cylindrical concrete structures 8 meters in diameter and 6 meters tall, open at the top, rest on the seafloor connected to 1,200 millimeter diameter intake pipelines. The velocity cap design limits intake flow velocity to 0.1 meters per second, low enough to allow fish and marine organisms to swim away from the intake rather than being entrained, a critical environmental compliance requirement under California's once-through cooling regulations. From the seafloor intakes, the seawater is drawn through the buried submarine pipelines by the suction of variable-speed vertical turbine pumps located at the onshore pump station. Each pump delivers 15,000 cubic meters per hour against a total dynamic head of 35 meters, powered by 1,800 kilowatt electric motors. A single large coastal facility operates 12 such pumps in parallel, with 4 additional pumps on standby, delivering a combined raw seawater intake of 180,000 cubic meters per hour to the pretreatment systems. Stage 2. Pre-treatment. Preparing the ocean. Raw Pacific seawater arriving at the coastal facility contains suspended solids, algae, marine organisms, dissolved organics, and the full biological complexity of the open ocean. Before it can enter the reverse osmosis membranes, which operate at pressures of 55 to 70 bar and are destroyed by particulate contamination, it must be reduced to a clarity that approaches optical purity. Pre-treatment begins with dissolved air flotation, a process where microscopic air bubbles are injected into the seawater, rising through the water column and carrying suspended solids, algae, and organic material to the surface as a concentrated froth that is skimmed and removed. The clarified water then passes through dual media filtration, layers of anthracite coal and silica sand in 4-meter deep filter beds, reducing turbidity to below 0.5 NTU. Final pretreatment is cartridge filtration through 5-micron polypropylene filter cartridges, removing any remaining particles that could damage the RO membranes. Stage 3. Reverse osmosis, the heart of the system. The pre-treated seawater enters the high-pressure reverse osmosis system, the engineering core of the entire facility, through high-pressure feed pumps that raise the water pressure from atmospheric to 65 bar in a single pumping stage. At 65 bar, approximately 940 pounds per square inch, the hydraulic pressure forces the water molecules through semi-permeable polyamide membranes while rejecting 99.7% of dissolved salts, bacteria, viruses, and trace contaminants. Each RO pressure vessel, a 300 millimeter diameter, 6-meter long cylindrical housing in high-pressure fiberglass, contains 7 membrane elements arranged in series, each element a spiral-wound sheet of polyamide membrane with 37 square meters of active surface area. The largest proposed California facilities contain 120,000 pressure vessels operating in parallel, containing 840,000 individual membrane elements, a membrane array so vast that laid flat, it would cover an area of 31 square kilometers. The engineering efficiency of the RO system is dramatically improved by pressure energy recovery devices, specifically isobaric energy recovery devices that capture the pressure energy in the rejected concentrate stream and transfer it directly to the incoming feed stream, reducing net energy consumption from 5.5 kilowatt-hours per cubic meter of product water to 2.2 kilowatt-hours per cubic meter of product water. Stage 4. Post-treatment. Making water safe and stable. The water emerging from the RO membranes is chemically pure to a degree that makes it unsuitable for direct human consumption, stripped of all minerals, slightly acidic, and aggressive toward metal infrastructure. Post-treatment restores chemical balance through a two-stage process. Limestone contactors, tanks filled with crushed calcium carbonate through which the water flows upward, dissolve calcium and bicarbonate ions into the water, raising the pH from 5.5 to 7.8 and adding the hardness minerals that make water palatable and pipe compatible. A final disinfection stage applies ultraviolet irradiation at 40 millijoules per square centimeter and residual chloramine addition, ensuring microbiological safety through the distribution system. Stage 5. High-pressure transmission, moving water uphill across California. Treated water leaving the coastal facility enters the transmission pipeline network, a system of 2,000 millimeter diameter pre-stressed concrete cylinder pipes installed in corridors paralleling existing California aqueduct infrastructure, carrying water at 20 bar operating pressure across elevation changes of up to 600 meters through the coast ranges and into the Central Valley. Booster pump stations at 50-kilometer intervals, each equipped with 4 variable-speed centrifugal pumps delivering 5,000 kilowatts each, maintain transmission pressure and flow against the topographic gradient. The transmission network operates as a closed pressure system. Water enters at the coast and exits at delivery nodes across the Central Valley, the Sierra Nevada foothills, and Southern California, 600 kilometers from the Pacific. The steel giants of the Pacific System. The scale of machinery required to construct and operate California's proposed desalination network has no precedent in the history of American infrastructure. The offshore intake pipeline installation requires derrick lay barges, vessels displacing 40,000 tons that operate as floating pipe-laying factories, welding 1,200 millimeter steel pipe joints, applying concrete weight coating at 80 millimeters thickness, and lowering the completed pipeline to the seafloor at rates of 2 kilometers per day. The mooring systems that hold these floating steel giants in position against Pacific swells use 12-point anchor arrangements with 250-ton anchors and 76-millimeter diameter chain. Onshore, the excavation and installation of the inland transmission pipeline requires a fleet of 52 Caterpillar 6015B hydraulic excavators, each weighing 150 tons and equipped with a 10 cubic meter bucket, working in continuous relay along the pipeline corridor, excavating the 3.5 meter deep, 3 meter wide trench at 400 meters per day per machine. Behind the excavation fleet, a pipeline string-out operation deploys side boom tractors, Caterpillar 594H units at 130-ton operating weight, lowering pre-welded 24-meter pipe strings into the trench at a production rate of 1.5 kilometers of installed pipeline per day. The high-pressure pump stations that maintain transmission pressure are themselves industrial facilities of imposing scale. Each booster station houses 4 vertical shaft centrifugal pumps in a purpose-built structure 80 meters long and 30 meters high. The pump impellers alone measuring 2.4 meters in diameter, rotating at 750 RPM, each delivering 20,000 kilowatts of hydraulic power to the water column. The pump stations are powered by dedicated 230 kilovolt electrical substations drawing from California's transmission grid. The entire desalination network at full production consuming 18,000 megawatts of electrical power, equivalent to the output of 18 large nuclear power plants. Engineering against the Pacific. The Pacific Ocean is not a passive participant in this engineering project. It is an adversary of extraordinary complexity and power, and every system in the desalination network has been designed in direct response to its specific threats. The California coast experiences significant episodic biofouling events, red tides, harmful algal blooms, jellyfish swarms that can increase the biological loading of intake water by a factor of 100 within hours. The pre-treatment system must handle these peak events without reducing plant output, requiring a design capacity of 150% of normal operating load and a chemical dosing system capable of responding to rapidly changing water quality conditions within 15 minutes. The Pacific's seismic context is equally challenging. The proposed pipeline corridor crosses the San Andreas Fault at 4 locations and the Hayward Fault at 2 locations, the 2 fault systems most likely to produce magnitude 7.0 or greater earthquakes in the coming century. The pipeline is designed with fault crossing assemblies at each location, sections of flexible bellows-type expansion joints capable of accommodating 2 meters of horizontal fault displacement and 0.5 meters of vertical displacement without losing pressure integrity, combined with automatic isolation valve systems that close within 30 seconds of seismic detection to prevent catastrophic water loss. The brine concentrate discharge, the 45% of intake seawater rejected by the RO membranes as a high salinity stream at 1.5 times normal seawater concentration, requires engineered diffuser systems at the offshore discharge points to ensure rapid dilution and minimize impact on the nearshore marine environment. The diffuser design, 200-meter-long pipes with 120 individual discharge ports at 5-degree upward angles, creates a mixing zone that achieves 1.1 times ambient salinity within 50 meters of the diffuser, meeting California's Ocean Plan water quality standards. The rebirth of the Western water economy. There is a version of California's future that does not involve this project. In that version, the megadrought continues unabated. The Colorado River Compact collapses as 7 states fight over a river that no longer carries enough water to satisfy any of their allocations. The Central Valley's agricultural economy, which feeds a nation, contracts by 60% over 2 decades. Las Vegas, Phoenix, and Los Angeles implement permanent water rationing. The internal migration begins. That is not an imagined dystopia. It is the projection of current trends published by peer-reviewed science and acknowledged by the governments of every state that draws water from the Colorado River system. The alternative, the Pacific Desalination Network, is an engineering program of a scale that American infrastructure has not attempted since the interstate highway system of the 1950s. It will require 30 years to complete, $3.5 trillion to finance, and a political consensus that has so far proved elusive. But it will produce something that the megadrought cannot take away. A water supply whose source, the Pacific Ocean, contains 710 million cubic kilometers of water and will not run dry in any human timescale. The ocean has always been there. California has simply been looking at it instead of drinking from it. The engineering that changes that is not science fiction. The membranes exist, the pumps exist, the pipelines exist, the energy systems exist. The only question is whether the will exists, the collective decision of a civilization to invest at a scale proportional to the threat in the infrastructure required to survive what is coming. The Pacific is waiting. The engineers are ready. For more engineering marvels redefining what is possible, subscribe to QuitTech Process. The secrets of civilization-scale construction are waiting, and we will uncover every single one of them.